Section 1-2, functions and their graphs. Now the goal in this section is going to be function analysis. Now we're going to analyze those functions in two different ways. We're going to start by analyzing functions graphically. We're going to identify functions using the vertical line test. We're going to identify domain and range based on the graph. We're going to identify intervals on which the graph increases and decreases. And then we're going to describe the symmetry of the graph, again, all simply by observing the graph. But then we're going to back up and do all the same stuff algebraically. We're going to identify functions. This time we don't use the vertical line test. That's specifically when you are looking at the graph. We're going to be able to just look at the equation itself and determine if it's a function or not. We're going to identify domain. We're not going to worry about range, though, when we're doing this algebraically, because when it comes to range, the techniques are a little bit more cumbersome, and once we get to calculus, it's going to be so much easier to find range. So we're just going to wait until we take calculus to figure out the best algebraic way to find range. We're also going to skip increasing, decreasing. Once again, calculus works so much better than pre-calculus for that, so we'll save that for then. And then we're going to describe symmetry, again, algebraically. So let's start with what a function is. Now, in Algebra 2, you talked about functions. You used function notation. So this is just a recap of what a function is. Remember that a function is simply a relation. Any rule that describes how you get from here to there is a relation. Now, in order for that relation to be a function, each input or domain value has to be paired with a single output or range value. So when I put something in, I should only get one thing out. So to be a function, every number I put in for x, I should get only one answer out at a time for y. So if I input 2 for x, then I should get a number out for y. And I should always get the same number out for y. If I put in 2 for x and I get 3 out for y, every time I put in x equals 2, I always get y equals 3 as the result of the function. As opposed to if I put in x equals 2 and my output could either be positive or negative 3, well then that's two separate outputs for one single input, therefore it would not be a function. Think of a function as cause and effect. If I do something, then it always produces a certain effect. So if I put in an x value, it always produces a specific y value. Remember that our notation, f of x, is our function notation, and it's just a fancy way of saying y. X is the input, y is the output. I put in an x value, I get out a y value. X is my domain, y is my range. Now, when I'm able to write that equation in that format, in other words, y equals some function of x, then we can say y is a function of x, or y is dependent on x. Now I could just as easily write equations, for example, x equals f of y, switch up the variables, in which case y would be the domain and x would be the range. What matters is this is the input, this is the output. So if x is the input, then y is a function of x, or y is dependent on x. If y is the input, then x is a function of y, or x is dependent on y. Whatever the input is what it is a function of. Now, vertical line test. Once again, you looked at this in Algebra 2, so let's see what you remember. Which graph represents a function by applying the vertical line test? Take a second, pause the video, give it a try, and then hit play when you're ready. Alright, let's look at each one individually. So, starting with the first one, does this represent a function? Remember that the vertical line test simply requires that you take a vertical line, or imagine a vertical line, passing over the graph. If that vertical line at any point on the graph touches the graph more than once, then it is not a function. And as we pass this vertical line over, hopefully you notice that at any random point, it was actually touching the graph at two separate locations. For example, at this specific x value right here, if I were to draw a vertical line, it touches the graph up here and down here. So for this x value, for this input value, for this domain value, it has two separate range values. It has two separate y values. If I plugged in x equals, let's say if this was x equals 5, the graph is showing me that the y value could be, let's say, positive 3 and negative 3 at the same time. So this one does not pass the vertical line test, thus it is not a function, because at a specific domain value, I have two separate range values. Now this one, as we cross that vertical line, past that vertical line across the graph, I didn't see any issues on this one. The vertical line only ever touched the graph at one point at a time, so this one passes the vertical line test. Here we have a circle, pass a vertical line over a circle, and just like that first graph, this one fails miserably. Now here we have what's called a piecewise function because we have basically two separate pieces that are not connected. Essentially what this is one function that obeys two different rules depending on what set of x values that you're using. Now notice there's a hole up here. That little symbol right there means there's a hole, and this is a dot. This is closed, so it's included. That's a hole, so it's not included. When I pass the vertical line over this one, it looks fine on this side, it looks fine on this side, but the question comes, what's going on right here at that specific x value? Now remember, it's not included up here, it is included down there. Therefore, technically, there is no overlap right here because it's only included on the bottom part of the function. So this one does pass the vertical line test. Now, if both of these were closed, top and bottom, that would have been a situation where it failed the vertical line test because of that specific point. But because one is open and the other one's closed, we're perfectly fine. All right, let's talk about domain and range. Now, we've already addressed it briefly when we defined function. Domain is the input, range is the output. Well, let's go ahead and define it a little bit more. Domain is the set of x values for which the function is defined. So when I'm saying what is the domain of a function, I'm asking what x values am I allowed to plug into the function. So what real numbers are you allowed to plug in and get a real number answer. So if I gave you y equals x, well, I can pick any random number I want for x and I would get a real number answer for y. Versus y equals 1 over x, I can almost pick any number I want to except for x equals 0, because if I plugged in x equals 0 for 1 over x, 1 over 0 is undefined. That is not a real number answer. So for y equals x, we say the domain is all real numbers. For y equals 1 over x, we would say the domain is all real numbers except x equals 0. Now we're going to start our exploration of domain and range again by looking at the graph. So remember what I said, domain is the x values that are used by the function. So if we look at this graph, remember that the x values go along in this direction. So each one of this graph represents an infinite set of points, and each one of those points has an x and a y coordinate. So we see if we look all the way to the left, we've got this point right here at x equals -3. And it travels to the right forever and always. It increases as it goes, but it travels to the right forever and always. It never goes to the left of x equals -3. It only goes to the right of x equals -3. So if we look at this a little closer, we can say that each one of these random coordinates represents a point on the x-axis. So as far to the left as it goes is -3, and it uses up every single coordinate on the x-axis to the right of -3, in other words, from -3 to positive infinity. Therefore, I can say that the domain is the interval from -3 to positive infinity. Now remember, we always put a parenthesis on infinity. -3, we have to make a decision, should it be a bracket or a parenthesis. The fact that it does actually get to x equals -3 means that we will use a bracket. So our domain of this function would be the interval from -3 to infinity, including the -3. Now we can do the same thing for range. If I think about this coordinate right here, which was at y equals -2, we're using every single y value starting at y equals -2. Now keep in mind, this graph technically goes up and up, 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 up forever. So even though just on the picture that I'm looking at, it looks like it may stop here, it actually does go forever up, up, up. So we start at -2 on the y-axis, we go up forever to infinity on the y-axis. Therefore, our range is going to look very similar to our domain, except it's going to start at -2 and go to infinity. So we have our domain of -3 to infinity, we have our range of -2 to infinity. And again, we did this simply by looking at the graph. We started on the x-axis at -3 and went to the right forever. We started on the y-axis and went at -2 and went up forever, domain and range. All right, now why don't you take a look at this one, see what you can figure out. All right, so we look at this one. One of the tricks for finding domain and range is to think about first off in just one direction at a time. So if we start with the x direction, if I think how far to the left does it go, how far to the right does it go? Now the graph has an arrow going off to the left forever, it has an arrow going off to the right forever. Therefore I know my left bound is negative infinity, my right bound is going to be positive infinity. And then I ask myself, are there any breaks in the middle? Now this is a nice, smooth, continuous graph. There are no breaks. Therefore my domain would be the entire x-axis from negative infinity to positive infinity. Now for the range, I can think of it in the same way. The arrow goes down forever, it goes up forever, so I know my boundaries are going to be negative infinity and positive infinity. And between the bottom and top of the graph, once again, it's perfectly continuous, so I am going to be using the entire y-axis. So once again, I have negative infinity to positive infinity for the range. All right, give a try on this one. Hit play when you're ready. Alright, so once again I'm looking for domain and range. Starting with the domain on the x-axis, I have an arrow going to the left forever and to the right forever. So I know I'm going to have negative and positive infinity as my boundary values. But then I look right here. There's this whole gap in the middle. Starting at negative 3, between negative 3 and negative 1, there's no connection in the graph. There are no x values being used between negative 3 and negative 1. So I'm going to state my domain, but this time I'm going to state it with a break in the middle. I'm going to start at negative infinity all the way to the left, and I go from negative infinity all the way up to negative 3. Now since there's a hole at negative 3, I put a parenthesis. And of course, since I'm going to have a completely separate interval, I'll throw in my union. And then my x-axis, my interval starts again at negative 1 and goes off forever to positive infinity. Closed at negative 1, so I have a bracket. Then we can do the same thing for the range. If I go to the bottom of the graph, this is the lowest point on the graph at negative 2. So I know my beginning boundary is going to be at negative 2. Again, though, it's a hole, so I'm not going to be including the negative 2. If I go to the very top of the graph, both of these arrows tell me that it's going up forever, so either one I could use as justification that my upper bound is going to be infinity. But then the question is, do I have any breaks in the middle? Now I remember this break on the x-axis, but this is only a break on the x-axis. If I consider this mapped onto the y-axis, we start at negative 2, and I'm using all of these coordinates with this part of the graph. And then once I get to here, I'm using these coordinates basically twice with this part of the graph and with that part of the graph. So there are actually no breaks on the y-axis between negative 2 and infinity. So my range is just one statement from negative 2 to infinity, open interval. Now, beyond domain and range, it's often useful to talk about where the function is increasing or decreasing. Now, we talked very briefly in the last lesson about what it means for a graph to increase or decrease. Increasing means we have a positive slope. Decreasing means we have a negative slope. Now, I put slope in quotation marks because slope at this point we've defined as the steepness of a line. Now, this is not a line, this is a curve, but it's helpful to think of it as if it was a line. So if I were to look at this point right here and I were to think of it as a line, and I were to flatten it out into a line, I would see that that is a line pointing up, versus if I looked at this point right here and flattened it out into a line, I see a line pointing down. So I know I have a positive slope over here, I know I have a negative slope over here, I know I have a positive slope over here. So we want intervals of where it's increasing and decreasing simply by starting to find where does it change from increasing to decreasing or vice versa. So we look at this point right here, and we look at this point right here. Those are the points where it changes, either going up to down or down to up. So if I were to, say, put a little point on the graph and have it travel along the graph, I can watch it increase slowly, and then at that point it changes to decreasing, and then it changes to increasing once again. So that's how I'm going to identify my intervals of increasing and decreasing, by simply identifying first where my maximum is, where my minimum is, and then splitting it up into its 3 separate intervals. So I have an interval right here, I have an interval right here, and I have an interval right here. So the two outer intervals are increasing, the middle interval is going to be decreasing. So we'll write our intervals always in terms of the x-axis. We're always going to use x-axis intervals in order to describe increasing and decreasing. We never use y values, we only use x values. So this maximum value occurs at x equals -2. This minimum value occurs at x equals 1. Remember, all the way to the left is negative infinity, all the way to the right is positive infinity. So that's how I'm going to describe my intervals. My increasing would go from negative infinity to -2, always a parenthesis on the infinity. Now, when we're talking about increasing and decreasing, technically -2 is an included value in the graph, but you can't really say it increases at -2. So when we're talking about increasing and decreasing, I don't really worry about brackets. I only ever use parentheses because, again, it doesn't make sense to say something increases or decreases at a point. It only increases up until you get to that point, because once we get to -2, it starts to decrease. So I'll put that over here. And it decreases until we get to x equals 1. And at x equals 1, it begins to increase again forever. So it increases from negative infinity to -2, decreases from -2 to 1, increases from 1 to infinity. So let's practice putting it all together. Let's identify for each of these graphs, determine whether it's a function, explain why. Remember, the explanation is pretty much going to be VLT every single time. Let's state the domain and range. We'll describe intervals of increasing and decreasing. We will identify extrema. Extrema is just a fancy word that means your maximums and your minimums. We will identify any intercepts, x's and y intercepts, and while we're at it, let's go ahead and describe symmetry. Remember, symmetry could be y-axis symmetry, x-axis symmetry, or origin symmetry if you're able to just rotate it upside down. So let's look at this one. So we can start by using the vertical line test. Think about whether this would pass or fail the vertical line test to determine if it's a function. And hopefully you are saying to yourself, yes, it is a function because it passes the vertical line test. Now, domain, if we look all the way to the left of the graph, notice it doesn't go forever. It actually stops at -4. So my domain is going to start at -4. And it's going to go all along the x-axis until I get to this point at x equals 1. We are including both of those endpoints, and we're going to have a separate interval starting at x equals 2, and since there's an arrow, it's going to go 2 to infinity. And this one's going to be an open interval since we are not actually including the 2. We can do the same thing for range. I know that arrow goes all the way down forever, but it is going to stop once I get to y equals 3. And notice right here, between -1 and -2, there are no y values being used, so I have a break. So I have range from -infinity to -2. That's going to be an open interval. And then we start again at -1. And we go up forever because of that arrow. Now we have increasing and decreasing, although at this point I think it's sometimes easier to skip ahead to extrema and then come back to increasing, decreasing. So extrema are all your high points and your low points. So right here, this is the highest point in its little area. So technically that right there would be our first maximum. So I have a max at the coordinate 1, 2, 3, 4. Oops, that's a 5, isn't it? That should be a 5. No one saw that. So we have a maximum at the coordinate -5, 3. Right here we have a minimum point at the coordinate -3, -1. Now at the tip of this little semicircle we have another maximum point because that's the highest point it gets to in that little region. So that would be at -1, 1. Let's add that to the maximums. Right here we have another minimum point because it's the lowest point in the region, so we have a minimum at 1, -1. And then if I look at this little area, here's where we get a little sketchy. Now, some might say, well, this point right here would be a maximum, but really it shouldn't be because it's not included within the domain. At x equals 2, I never actually reach that maximum. Therefore, we can't include it as a maximum of the graph. And the same thing with the arrow. That goes down forever, so you might say, well, we have a minimum, but then the question is, well, where does that minimum occur? It goes to infinity, which we never actually reach. So when we're looking for maximums and minimums, you're only allowed to include specific domain values. If it's not within the domain, then it technically does not count as a maximum or minimum. If you never actually get there, then you can't count it. So we have essentially our intervals. So our first interval, this line right here, from -5 to -3, it's clearly going down, so we have a decreasing interval from -5 to -3. Then from -3 to -1, we are increasing. And then from -1 to +1, we are decreasing again. We skip over 1 to 2 since that's not in the domain. We are neither increasing nor decreasing. But once we get to x equals 2, it decreases forever from there. So we will add that to our decreasing to infinity. Notice we are using +2, not -2, because these are x values, not y values. Next thing would be intercepts. So I can start with my x-intercepts. Feel free to approximate these values. I have an x-intercept right here, an x-intercept right here, and an x-intercept right here. I have 3 x-intercepts. So that's 1, 2, 3. So one, it's about -3.5. I have an intercept somewhere around, let's call it 2.75. And one somewhere around, let's call it 1.8. So those are my x-intercepts. I only have one y-intercept right here. Let's call that 1.8 again. So we have a y-intercept at 1.8. Now as far as symmetry goes, we're just looking to see x-axis, y-axis, or origin symmetry. And looking at this graph, I don't see any symmetry, so I'll simply just say none. All right, and there's the whole thing in a nutshell. Let's try it again. All right, here's one for you to try, and hopefully this one looks a whole lot easier because it will be a whole lot easier. Give it a try. So, trying the vertical line test. Now remember these lines right here, those dotted red lines, those are not part of the graph. Those are asymptotes. Asymptotes. Those are lines that the graph approaches but never crosses. So if I were to apply the vertical line test, as far as the blue portion of the graph, it never actually touches that graph more than once at a time. Even when it goes almost vertical right here, it never actually gets to be vertical. It just keeps getting closer and closer and closer to that y-axis. So yes, it does pass the vertical line test, if not barely. Alright, so domain, I see this arrow going to the left forever. I see this arrow going to the right forever. So I see almost every single x value being used except where that asymptote occurs. There we have an asymptote at x equals 0, so I can say the domain is all values except x equals 0. Now I can write that domain in either interval notation or set notation. If I write it in interval notation, I would write it -infinity to 0, union 0 to infinity, to describe all x values except for 0. Since 0 is not included on either interval, then we say 0 is never included in this interval. Or what actually is a little bit easier, if I just say it's all real numbers except x cannot be 0. That actually might be quicker to write when we have just a single value being excluded. And the same thing with range. I go down forever, I go up forever, but at y equals 0, I'm never actually using that value. So I can say that the range is all real numbers where y cannot be 0. Be careful when you're using that set notation for domain and range. It's quite common to forget that you're answering a range question and just say x cannot be 0 again. Range are y values. Make sure you say y cannot equal 0. Alright, so now for increasing, decreasing, extrema, let's start with extrema, looking for maxes and mins. Now I see that this goes down forever, but we're not allowed to include arrows as a minimum or a maximum. It's the same thing over here. Now this goes to the left forever, this goes to the right forever, but I don't see any clear turning points. I don't see any boundaries. I don't see any stopping points where it goes up, 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 and stop. I don't see anything going down, 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 and stopping. So this one actually has no extrema. So if there's no extrema, typically what that means is that it always either increases or always decreases. Extrema is where you change from increasing, decreasing. So if you never change, then we must always be doing the same thing. So let's look at the graph. If I start all the way to the left and I imagine some guy walking along that graph, hopefully you're going to see, well, he's probably walking down. So if I follow this graph from left to right, I curve downward all the time. Even when I skip over the asymptote and jump up here, I didn't technically increase to get up here. The graph just stopped existing and started existing, so I didn't actually do any increasing. I just started up at the top and I continue decreasing. So at any point in this graph, it is always decreasing. So it decreases from negative infinity to positive infinity, and it never increases. As for intercepts, I've got those asymptotes on both the x and y axes, so that means it has no opportunity to cross the x or y axis, so no intercepts. And symmetry, hopefully we see that this top one and this bottom one look almost exactly alike. They're not symmetric across the y-axis. They're not symmetric across the x-axis. This is origin symmetry, because I could rotate the graph upside down and it would look exactly the same. So it's symmetric around the origin.